Hello, everybody. This is Professor Ma, and this is the sections more about areas. And uh, these are the things we're going to talk about. Uh, going to talk about the distance, the how we measure, what's the basic procedure for measuring vertical distance and horizontal distance. Now we're going to talk about two different type of regions depending on the way the boundaries are and how do we set up the integral for these areas. Uh, so, uh, well, let me start out with a very basic observation about a real line. So we usually when we put on the real line, we have to the right hand side is the positive directions. And if I have any 2 points on the real line, their distance, it's the right hand point subtract the left hand points, always. If you do the other way around, you're going to get a negative numbers. Okay, so so if you want to get the positive distance, make sure you take the right hand mark minus the left hand mark. Usually that's the x coordinate. Now, if I turn the axis vertical and pointing upward as positive, and I have 2 points on vertical positions. If I want to find the distance between the 2 points, I will take the top point, the coordinates, subtract the bottom point coordinates. So it's a top, high minus low, if you like. Okay. So for instance, if I have these 3 points over here, and if I want to say, oh, what's the distance between the points, that's for instance, different point between, say, P and Q is the horizontal distance, is this coordinate subtract. Between R and P is the vertical distance, you subtract the Y coordinates. So there's order for this is important. So the sign, you wouldn't run down with the wrong sign. So suppose now about areas, suppose we have a shape like this and we want to find area. And so the first things I do is I take tape measures and I measure from one end to the other end. So from A to B. Let me remind you, it doesn't have to be like nicely horizontal. I mean, if I want, I go measure, say from this, from A to B from here, up here to B, up down to over here. So the shape, it doesn't matter, no particular orientations in these particular examples that's required. Okay, so let's say we measure from A to B on our ruler. Okay, and the important things is can we extract the cross-section directions across the ruler, vertical direction across the ruler, the length across the regions. Okay, and that's the function we would like to get our hands on. Okay, suppose I know that. Let me call that length function L of x. Okay. So, and now I'm going to use that function to approximate the area R. Use a bunch of rectangle, and just like we did last time, we're going to use use the partitions of the intervals, and we're going to use rectangle base on the sub-interval each one, the partition, using the height of the length, cross-section length at each point, and make a rectangle, okay? And with the spacing delta x. And I paste these rectangles all the way from one end to the others, strips of rectangular pieces. Then I add up the rectangular pieces, and that's approximations of the area with these rectangular strips. Okay, and remember, this is what we call a Riemann sum. Okay. And then the theorem says, fundamental theorem says, if I take the limit as delta x go to 0, take skinnier strips, Okay, so this area becomes thinner and thinner, like streamers on decorations in the thinner, almost like a thread, but still has some area it covers, and so on. When delta x go to 0, that's the area of R. So in other words, we have these theorems, and the regions R, of a two-dimensional region, is the definite integral. Okay, it's definite because we have the boundary A to B. We're going to get a number out of it. The integral of what? Of the cross-sectional length function, the L of x. Actually, another way to look at it is this. Instead of just looking at L of x, we look at what is L of x times dx. Okay. We can think of L of x, again, cross-sectional length. The dx came from delta x. You can think of this as a very thin little strips with delta x. Okay, so therefore, this is a very thin strips of area. Okay, later on we will call this the differential dA. Okay, a very infinitesimal area, strips of area, and we are adding numbers. The fundamental theorem basically we are adding, and since we're adding infinite many of them, it turns into an integral. Okay, so we're adding all this small strip area. So that's one of the key points of this formula. Okay, that the area is the definite integral of the cross-sectional functions. So here's examples, and so if I were to put the rulers down, so I need to find out what intersection points are between one end to the other, and solve the equations equal to each other's, and so on. So I find the x equal to 0 and 1. So therefore, it starts from 0 here, it goes to 1. So in between those two markers. And then I want the cross-sectional length. Well, the cross-sectional length is, well, here's where we are going to use that rule. It's going to be the high points subtract the low points, the height. Okay, it's going to be, which one is on top? The green one. Okay, so it's going to be minus x squared plus 2x. Subtract the coordinate of the red one for the y coordinate. So this is again, this is high minus the low. Okay. And then the rest is integrations. We guarantee the answer is going to be a positive. Is the area. Okay, in here there's no sign error. We're not talking about the other cases. In here it's guaranteed because of the order of subtraction, things are positive, we're going to get a positive answer, which is the area. Okay. Here's another example, and I'll leave you to graph. This is the actual graph. First, we want to find out what the area is as, or the area in between the red curves and the green curves. Okay, and notice the point about this question is that this really consists of two different problems because the crossing. In this piece, the top points, the top is the green line, but after the intersection, the red curve is the top points. Remember, we have to subtract in order. So therefore, you have to break this into two different pieces because on the left-hand side, the green is in the front, formula is in the front, and on the right-hand side, the red formula is in the front. So there are two different sets of calculations. Of course, first we have to break them into two different pieces, find out the intersections, and this is done by setting them equal to each other and solve for x, and therefore we have on the rulers we have from -1 to 0 and 0 to 2. Then we look at individually the pieces. Okay, the first one, A1, area number 1, the green one is on top, so therefore minus x squared. The green curve, it goes in the front, and then the red curves is the bottom coordinates of the y coordinate, top minus the bottom. So that's the area for that small piece. What's the area for the large piece? What the area for the large piece is the other way around. Okay, then you do these two separate calculations. And the rest is just do the integrations and plugging numbers, and I'll leave that up to you to check the arithmetic. Okay. Now, this comes to two type of region of which we're going to use and address quite a bit from here on. Yeah, somewhat from here on, especially in carry out to 267 3D. The two type of region depends on how the boundary of the region are defined. Okay, and the basic geometry we're going to use in here is that suppose I have a formula, a curve given by equations, given with x's and y's all mixed together, not necessary functions. Okay, x squared plus y squared. Okay, stuff like that. If I want to know the vertical distance, okay, at a point, well, then I look at the y coordinate. Then basically, then at a point x, the vertical, given an x, the vertical distance to the point is a function of x. You want the y in terms of x. Okay. But if I want to know the horizontal distance, the point to the y-axis, then I want the x coordinates. Okay. So at a given point y, if I want to know the horizontal distance at the level y, I need to solve the x coordinate in terms of y. Okay. So for example, here's a curve. I can, it says, okay, find out, express y as f of x. Well, here's a graph of the curve. You solve for the y. I mean, we solve y in terms of x, but you get two of them, right? You solve y, you get y squared, y is equal to plus minus y to x plus 4. But here it tells you y is positive, therefore it's not a negative, therefore it's positive. Okay. So if you know the picture of this, if you want to graph, if you want to look at what this graph is in terms of these, and this is it is 0, when x is -2. When x -2, you get square root of 0, square root of 0 is 0, so it starts with -2, 0. Then it just goes as a square root functions. Okay. When x is 0, y is 2. Okay. So this is the curve for this formula, the square root formula. So given an x, then the vertical height is root 2x plus 4. Okay. Then given the point, any point xy, what is the, given at y, what is the horizontal distance x? Well, then in that case, you want to solve x in terms of y. And these cases have here it is. Okay. It's easy, you can see the algebra. Okay. And why are we doing this? Because now we're going to keep track of the type 1, type 2. Type 1 concerns vertical distance. That is easy. Okay. So here's type 1 region. The type 1 region is that I know the top and bottom boundary. And therefore, if I need a distance between the two boundary, all I have to do is subtract the y component, the high points, the y coordinate of the higher point, subtract the y of the lower point. And y component are functions in x. So in this case, I subtract f of x minus g of x. And that would be the length functions. Hence, the integral is from a to b, top functions minus the bottom functions. X goes to b. Like this. Type 2. Now the boundary is to the sides. Okay. On the right-hand side, I know the horizontal distance. A point over here, given a y, and I have the red color. I mean, here I got x of fy, right, and given a y, and a point over here, again, is at a height y, except this is what? G of y, right? X is g of y. Oops, not very good. X is equal to g of y. Okay, allow me to write over. If I want to know the distance, the right-hand side, f of y, subtract the left-hand side. Remember, right minus left. So it's f of y minus g. Okay. And then it goes, y goes from c up to whatever d is, that you have this cross section. Remember, the ruler doesn't have to be this way. The ruler can be this way, c to d. Okay, but we usually call that the vertical y coordinates. Okay. And this particular example actually I can do it both ways. So I'll leave it up to type 2. We did type 1, but you can figure out how to do this in type 2. And here's examples that which if you do it in one way, it's more difficult because more work. But if you do it the other way, it's less work. If I do this at type 1, if I use vertical, if I use a vertical subtraction, find the vertical distance, and that we have a problem with a corner. What corner? Here. Why? Because the top is the same thing, but the floor, the bottom, as we go from the bottom, the top minus the bottom, top minus the bottom, when we get this point, the bottom change. I have to use the top, subtract now a different functions, okay, to get a bottom. So there are two different sets of formula because the bottom points formula change into two parts. So as type 1, I need to do in two pieces. Here is the first piece. Okay, here's the second piece. Okay, and root x is the top. The bottom is 0, so root x minus 0, so I don't have to write over here. And when I get over here, well, now the bottom piece is x minus 2, therefore I have to subtract out into another piece. So this is two sets of calculations. Okay, then we integrate it. But if I realize as type 2, okay, you see there's somewhat a bit of antiderivative you have to sit down and calculate, and arithmetics and etc. Okay, but if you realize as type 2, we solve everything in terms of letter y. We get a right-hand x. So a point, so one distance like from here to here. So I find the x over here and subtract the x over here, and this of course, and so I solve this in terms of x of course is y. Oops, so if x is y plus 2, okay, on the line, you see here it is. And I subtract the x component over here is x equal to y squared. Here's y and y. This time I subtract the x coordinates in terms of the letter forming the y's. Okay. So, and then I can integrate it from the y go from 0 up to 2. Okay. So think about it. Okay. And this y plus 2 is the x coordinates of a given y. Okay. And this y square, it should be the red color is the given the y, and what's the x coordinates? And you take the difference. Okay, that's it. And bye bye. Until next time. Do home.